how to use the residual theorem to calculate the trigonometric function and rational functions. Now we have the third type of this function. We call it trigonometric rational function, which means we combine them together. For example, I give you a example. This example, e to the power negative ix over x squared plus 1 dx. Now maybe you will be quite confused that there's no trigonometric function, but as we can see in the numerator, we have this term, and we know that all the trigonometric function we can convert them into the sine and cosine, and sine can be written as e to the power e to the power ix minus e to the power negative ix over 2i, and cosine x we can write it as e to the power ix plus e to the power negative ix over 2. So finally, we can all convert this function into this type and this type to the exponential function. So we only need to figure out how to calculate this integral. Then we can solve the trigonometric and rational function, their combination. How to do this? By residual theorem, we will see. Okay, this is what we call the improper integral. Improper integral. And we can write it as limit r tends to infinity, r negative r eix over x squared plus 1 dx. Right, sorry, negative r. And we have the line, straight line is negative r, positive r. And we want to calculate, we want to integrate this function through this straight line, and we found that it's not so easy because it's hard to find the antiderivative of this function. And so the next step is we try to construct a semicircle. Like last time we mentioned, we try to construct a semicircle to make the straight line into a closed contour. Then we can use the Cauchy-Gorset theorem, or its corollary. We call it the residual theorem. Okay, let's see how to do that. And firstly, we need to see, okay, we need to construct a contour to, to update it into the two-dimension complex plane. So, okay, we can change negative r to r. We can change it into the contour gamma r. It will be the contour integral, and change x into the z. Iz over z squared plus 1 dz. Okay, so it become a contour integral. Now it's the time for us to choose which semicircle we need. We need the upper semicircle or lower semicircle. Okay, we first use the upper semicircle as an example. We have to try, is it workable? Upper semicircle. We see if we choose the upper semicircle, let's see the numerator EIZ. Z can be written as x plus iy is equal to, we take the norm, ix plus iy, and it will become ix plus minus y, isn't it? And we will find that as e to the power ix we take its modular, it will become to 1. So we only have this remainder. Okay. What does this mean? Oh, sorry, it should be negative. Yeah, it should be negative. There's a typo. It should be negative there, negative and this is positive, negative, negative. Here is the positive. If we choose the upper semicircle, we will see when r tends to infinity, we can take y equal to r. This will tend to infinity, which will make this integral divergent. So it's not convergent. So we cannot choose the upper semicircle. So we only can choose lower semicircle. Lower semicircle. So we will choose the lower semicircle to be our contour. Oh, sorry. Lower semicircle CR negative, and from negative R to positive R, isn't it? And after we choose this contour, it will be gamma R CR negative. And let's do the calculation. And okay, our target is to figure out this integral, and we can see we can convert gamma R, I denote it as Fz, into the closed contour, right? Closed contour, gamma R plus, this is gamma R, this is the orientation, and this is the orientation, so negative CR negative, Fz dz plus, we minus 1, we add 1, so we need to minus it, CR negative, Fz dz, isn't it? Okay, after we choose this, we will see we first need to figure out this integral, and this is a function in the closed contour, and it's a simple closed contour. And what we need to do, we need to figure out its singularity first. If there's no singularity, then by Cauchy-Gorset theorem, it will directly become to 0. But if there is the singularity, we need if there is a singularity, then we have to use the residual theorem. So let's check. Fc is equal to e to the power negative iz over z squared plus 1. And we check this plus 1 to 0, then we can get z is equal to positive negative I. And we choose what? We choose the upper lower semicircle. So we only have one singularity here. Negative I, positive I is at the upper part. And we only need to choose z equal to negative I will be the singularity. Right, so by residual theorem, this part Ez will become to 2 pi I 2 pi I times res f negative I, isn't it? And we found that it should be the pole of order 1, the pole of order 1. Order 1. So hence the residual will equal to limit we take z tends to negative I, z plus I times fz. Fz is e negative iz, z squared plus 1. Right, then we use the L'Hopital's rule. Sorry. The denominator will become 2z and the numerator will become let's see, z plus I take derivative, e negative iz, and this part take derivative, negative I, oh sorry, what's going on? Okay, negative I e I z negative z plus I, and we, oh sorry, limit z tends to negative I, we plug negative I inside, it become negative 2i, 0, this one will become 2e, right? Negative I times negative I, oh sorry, oh, isn't that? Will become to this part. Let me see the answer. Okay, yeah, I'm correct. So negative 2ei 1. Okay, this is the residual, and we plug in, it will become 2 pi I times negative 2ei 1 over negative 2ei, 2i cancel out, negative pi over e, isn't it? Okay. Oh, sorry. Yeah, I believe I'm correct. Um, negative 2 pi I. Yeah. Okay. Let me check. I believe it's correct, but let me check. Yeah. Okay. It seems like there's a negative here. Okay, no worry. I know. We see here. This is the contour, right? This is the contour, and the orientation is clockwise. So when we find the one number, we just draw a straight line. Oh shit, straight line. Okay, okay. We will see it enter from the left. Let the number that it crosses from the left is 1, and by the definition of the wing number of the wide number, it will be right minus left. So the number that the how to say the curve cross the straight line from the right is 0, minus left is 1, so it's 0 minus 1, it will become 2. Yeah, and we will have a negative here times one number, so we will have a negative here, and negative cancel out, it will become positive. So the answer is pi over e for this integral. Okay, let's check the next part. Is we have finished half of our job and we still have this remain, right? And what's this? Gamma r f z dz. Okay, let's see. Gamma r, and what is f z? F z is e negative iz over z squared plus 1 dz. And we will find that, okay, it's not a closed contour, right? So we cannot directly use residual theorem or Cauchy-Gaussian theorem or Cauchy integral formula. We need to find another way. And as we see that, let's first observe the numerator, e to the power negative iz. I have said if I take the modular, it will become 2. Okay, I use an inequality first. Okay. it will less than or equal to, we take absolute value of it, right? No problem, isn't it? Okay, and by triangular inequality, less class meeting, we mentioned about that. It will less than or equal to, I take the integral for the I take the absolute value for the integrand. Iz over z squared plus 1, isn't it? Let's first observe the numerator. If Iz, right, is will equal to e to the power y, right? And what is y? Y is less than or equal to 0. Why? Because we take the lower semicircle, oh no, only less than 0, no equal, right? We take the lower semicircle, and y will belongs to this part. Oh yeah, we can take 0, and the r is got from these 2 points. We will see y will equal to 0, right? And anyway, y will less than or equal to 0, so which means this part will less than or equal to y, isn't it? If you draw the picture, less than or equal to 0, this is 1 for the exponential function, isn't it? Oh, okay, so we will see this one will less than or equal to gamma r 1 z squared y plus 1 d z, isn't it? Okay, how to prove the rest parts? Because the z is on the circle, so gamma z, so the modular, or we take the norm of z will equal to r. At z squared plus 1 will greater than equal to r squared minus 1 if we take its inverse. 1 absolute value less than equal to, isn't that? Both sides we take gamma r, dz, this is a constant. We take integral, this is a line integral, right? So it will equal to gamma r pi r over r squared minus 1 dz, right? Isn't it? Okay, I move it here, and we will see finally we get this part, gamma r pi r over, oh no, there's no the integral sign, right? We have done the integral part. Y will less than equal to pi r over r squared minus 1. So this is the so this is the final right hand side for this inequality. We will finally get gamma r f z dz, take its absolute value will less than or equal to pi r over r squared minus 1, isn't it? Take its norm, and this is norm, so it will greater than equal to 0. And r tends to infinity, this part will tend to 0. It's easy to figure out, right? Just use the L'Hopital's rule or whatever rule you want, it's easy. Okay, it tends to 0 and 0. So by squeeze theorem, this one will tend to 0, right? Will tend to 0 when r tends to infinity. So hence we know that limits integral gamma r f z dz when r tends to infinity equal to 0. Okay, so hence we can get the answer. Okay, where it is? Let me check. Yeah, this integral. Negative, infinity, positive, infinity. Okay, x squared plus 1 dx, the real integral. We transfer it into a contour or complex integral. Gamma r f z dz, and it will become to the two parts r tends to infinity, gamma r plus negative cr negative fz dz plus gamma r fz dz This one 0, this one we calculated, right? Pi over e. Hence the answer is pi over e. Now that's all for that.